All right, appraisers, this is Brandon with Spark for Appraisers, and this video is going to cover error, a couple different error scores that we are going to include in Synapse. This is just one more indicator that you can use to rely on in order to help you determine what methods in Synapse may be better to place weight on. There are, of course, a lot of factors involved. You may have a really low, in error scores, lower is better, a really low error score, but perhaps it's based on data or properties that are not super similar to your subject property. So maybe even though it has a better error score, you might still want to place weight on a different data set that maybe has a slightly worse error score, but is based on properties more similar to your subject. It's kind of just, there's other things at play. You as the expert will need to take those into consideration when you're determining this. We're going to provide these error scores and show you which method or result had the best or lowest error, but that doesn't necessarily mean that you should place all your weight on that method or even any weight. So again, it's there, it's helpful. It can help you determine what might be best to place weight on, but it's not the end all be all. Just like everything, just like standard deviation, R squared, all that stuff, it's not necessarily telling you what you should choose or place most weight on. Okay, so that being said, let's go ahead and get into the error scores that Synapse will calculate for you. So right here, what you have on the screen is a basic scatter plot I just made up, and I made up a y equals mx plus b. This is basically the formula for that purple trend line that you see on the screen there. The blue dots are the actual data points or the closed sales in your data set. Again, this is just made up data. So this is essentially a single variate regression analysis that calculated this purple trend line. Now in Synapse, we are going to use mean absolute error. And you calculate that a specific way. It's actually not very complicated. And in paired sales and sensitivity, you can also calculate it, but it's calculated just very slightly differently. I'll get into the differences at the end, but for now, let me just show you how it works with regression using mean absolute error. Okay, so let's go ahead and get into it. It's, as I said, mean, excuse my horrible handwriting, mean absolute error. You can abbreviate that as MAE, and that is equal to, and basically what it is it's calculating the difference between the predicted sale price and the actual sale price. It takes the average of all of those for every data point you have here. So let me show you what the formula would look like. So it'd be the sum from, let's see, I equals 1 up to n, where n is the total number of data points or total number of sales in your data set. And it's the absolute value of y sub I minus x sub I. All right, so basically the absolute value of the predicted sale prices minus the actual sale prices. You add them up. That's what this symbol means. You add up all of those, and then you divide by the total number. And that probably sounds familiar. Whenever you add something up and divide by the total number, that is the same as the average. And that's where we get mean right here. That's why there's the word mean in the name of it. So mean absolute error, and absolute obviously because we're taking the absolute value. So just to give you kind of a visual example of what that means, let me just choose like a bright pink here. So what this is, this y sub I minus x sub I, is actually the residual. And residual is the difference between what the actual sale price is and the predicted sale price. So that difference is that line right there. And maybe in this case, it's just making up numbers, $8,000. And then this one's a bit bigger. So that difference from the sale price of the actual sale price and the predicted sale price, which was down here, that difference is larger. Maybe that's $16,000. And there's no negatives because you take the absolute value, so everything becomes a positive. So all our numbers are going to be positive. And so we do the same thing, find the residual there, 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 and there, add them all up, divide by the total number, and that's our mean absolute error. So what that is it's an error score, and again, lower is better, and it's any number from 0, which would be no error at all, to infinity. So there's no standard. Like when we talk about r squared has to be between 0 and 1. there's some upsides and downsides to that. Upside is you kind of know the ballpark of your range, and everything is sort of standardized to somewhere between 0 and 1. But then the downsides are that it can make you believe that just because you have a quote unquote low R squared, maybe something below 0.5, that means that the results aren't very accurate. With mean absolute error, it could be anything from 0 to infinity, so it's all relative. You could have an error score of 2,000 or 100 or 10,000, but it's just all relative to the other methods. So if your other methods are right around the same area, or if maybe they're all a bit higher, that would mean that in relation to all the other methods that were run, this one that you're looking at has the best error score. It's not really telling you this is a great error score or this is a horrible error score. It's just saying it's better than the other ones that were run. There aren't a whole lot of absolutes when it comes to reconciling data. It's your opinion. And so this mean absolute error gives you an error score that you can opine on, and maybe it's going to be helpful in determining what appraisal methods you want to place weight on when Synapse calculates the results from all the different methods, or in some cases it might not be, but it's just another indicator for you to look at in addition to things like, standard deviation and R squared and the final result itself. So anyways, it's just there to be one more helpful piece of information for you. Now, one other thing I'm going to show you that we will do is we will also, let's go to green. We also are going to calculate the standard, this is going to be a mouthful, by the way, the standard error of the mean absolute error. And yes, that's a lot, but it's a really simple calculation. It's just the mean absolute error, whoops, divided by the square root of the total number of properties. What this does is it allows us a way to place weight on data sets that have more data in them. And so, for example, if we ran, let me just give you a quick little example here, just a quick little thing. Let's say we had 3 data points and our regression line was like that. Actually, it would probably look more like that maybe. Then we might have a pretty good mean absolute error score. I mean, this is all relative here. I don't have any coordinates on the axes, but I might have a pretty good mean absolute error score. But the fact that this is based on just 3 points of data means that we might not want to place a lot of weight on that because it has so few data points. And so this, for example, that line might give us a result of, let's say, $80 per square foot as our adjustment based on 3 data points. But if now here, I'm going to get rid of all that. But if it turns out this, instead of being what was this line, now with all these extra data points, it turns out our line would be like that. So I kept the same original 3 data points, I just added more, and that gave us very different results. So if this line was an 80, this line might be only $40 a square foot, so very different results. And this second line has probably more error, but it's going to have either a similar or a lower standard error of the mean absolute error because it's going to allow us to divide by the square root of the total number of properties. So in a real life situation, this first data set maybe would have, I don't know, let's just say 9 properties, and the square root of 9 would be 3, so we'd be dividing by 3. Whereas in this other one, let's just say in a real life situation, it was 36 properties or 36 sales, then we would be dividing by 6. So instead of dividing by 3, we'd be dividing by 6, and most likely that would take our error score for the results with far more properties lower than the one that was only based on 3. Again, it's not perfect because, like I said in the beginning, you may want to still place more weight on the data set that had very few properties in it because maybe those were most similar to your subject properties, so you think that's a better indicator. Again, I'd be careful with only 3, but assuming you have at least 10 or more in there, then maybe that's what you want to do and not place so much weight on the standard error of the mean absolute error. But it's just there as, again, one more indicator for you to possibly rely on. All right, I just now want to give you an example of using this with paired sales and sensitivity because they are slightly different. So I'm just going to erase this over here, and we will modify this formula slightly. And actually, it's very slightly by just changing one variable. So let's go ahead and draw that in here. So I'm going to, because it's a little different, I'm just going to use a slightly different shade of blue here. And I'll say for paired sales and sensitivity, you add up again from 1 to the total number of properties or paired sales. So in this case, if we're talking about paired sales, we're not adding up the total number of actual sales in the data set. We're adding up the total number of pairs because that's what the analysis was done on. That's how we got our result. And so the primary difference is we're taking the absolute value of x sub I minus mu and dividing that by n. So again, you can see very similar. Really, the only difference is we're swapping out y sub I for mu, and we'll get into the difference with what mu is. And keep in mind, it doesn't matter if x is on the left or the right of the minus sign since we're taking absolute value. So that part doesn't matter. And so now, just to kind of explain what mu is, let's go ahead and give an example. And this applies whether we're using sensitivity or paired sales. But let's just go ahead and get into the example of paired sales. Let's say we have pairs and they are 1, 2, 3, and 4. So let's say we only had 4 pairs. Maybe there was 20 data points that got us a grand total of 4 pairs, or maybe it was 50 data points that got us a grand total of 4 pairs. And let's say that those pairs, and let's assume we're measuring GLA, let's say they gave us $80 a square foot, $70 a square foot, $50 a square foot, and $55 a square foot. That's our result. Those are our pairs that we got. And in Synapse, it will take either the average of all of those or the median. Or a better way to say it is it will take the average of all those and the median and show you both numbers for you to decide which you prefer or which you want to place more weight on. And so basically mu would represent the result from that paired sale analysis. So if you're using average, it would be the average of all these numbers. Or if you're doing median, it would be the median of, again, all of these numbers. Oh, that was median of all those numbers. That is how we get to mu, is either average or median of those numbers, and that gives us mu. So again, we take the actual sale price, which is x, and that's what x is over here with regression as well. We subtract the average or the median, depending on which you're using in Synapse, and then we divide by the total number of pairs. So in this case, n would be the pairs, not the data points. And that's it. Otherwise, it's the exact same thing as we just talked about when it comes to regression. And then with sensitivity, the difference is, if you'll remember in sensitivity, well, broadly speaking, sensitivity is looking at which adjustments would give you the adjusted sale prices that are closer together, meaning the range, from low to high is the smallest number possible. And let's just say $60 a square foot led to the smallest range in total adjusted sale prices, then it would do the same thing we did with the pairs here, but it would take the average of all of those adjusted sale prices. So right here, you would have the adjusted sale price for data point 1, adjusted sale price for data point 2, 3, 4, and so on until you have it for all properties in your data set, and then it takes the average of those, and that is the mu. In this situation with sensitivity, we don't do the median, we just do the average, or you could say the mean. So that's what mu is. Otherwise, all the calculations are the same. Those are the error scores that Synapse will have, at least initially. Hopefully that helps everybody understand the way the error scores in Synapse will work, and we look forward to talking to you in the next one.